Good morning, everyone. So welcome to a new seminar from the MIST community. So, apologize. We have the pleasure today to have Maria Teresa Walach from the Lancaster University, and she's going to be talking about, I believe, about SuperDARN radar, so about the ionospheric electrodynamics at Earth. Just to give a bit introduction about her, so she did her PhD at the University of Leicester with Steve Milan, and then she moved, apologize, oh wow. And then she moved to Lancaster as a postdoc, and I believe she has been there since 2017, so it's like quite a long time now. And yeah, so Maria, when you want, please start.
Okay, thank you all. Thank you, Beatrice, and thank you all for coming. It's my pleasure to talk to you all today, not in my capacity as MIST Council, but about the science that I do every day. And I'm going to be talking about ionospheric electrodynamics. And as Beatrice already said, I'm going to be putting that into the context in particular of SuperDARN measurements. And so we're going to focus on the high to mid latitudes. So I want to start with this very basic view of the Dungey cycle. I'm sure many of you will have seen this already in the past, but this is quite important when we consider the entire system. And I'm going to be talking about global scale dynamics. So I think it's important to highlight this to begin with. So what we're looking at is a very simplified view. It's obviously not to scale, and there are two different schematics on this slide. The one on the left, we're looking at the Earth side on, and we have the sun towards the left. So the solar wind is coming in from the left here. It hits the magnetopause here. So there's the magnetospheric boundary where we get reconnection, especially during Southward IMF. In this purple region, the magnetic flux of the Earth is then opened and pulled towards the night side by the solar wind, where eventually in the night side in this purple region, it will reconnect again and then move back towards the day side. So this is the cycle of day side driving, which opens polar cap flux, and then night side reconnection closes it again. The magnetic flux lines of the Earth here, I have color coded them, going from blue to green, and then from green to blue, but back. And the reason for this is to make it easier to see what happens in the ionosphere. So if you're looking down at the magnetic pole, this is what you see in the northern hemisphere. You have in towards the top here. The magnetic pole would be somewhere in the middle. And we have, again, the colored lines here showing you this transport of plasma that happens as a result of this Dungey cycle. Now, when Dungey first came up with this in the 60s, he imagined day and night side reconnection to be balanced, and he imagined this to be a steady process. We since have learned that this is not the case. We know that the two can be unbalanced, and we know the two reconnection rates that we know that there are other dynamics in the system which cause asymmetries, especially in this flow pattern. And we're going to be looking at some of those today. So this is my slides that I've taken from ESA, and this is primarily about space weather, this slide. And we can see here, there's various things highlighted here. And the reason why I've put this up is because geomagnetic storms are often talked about in relation to space weather. Today, I want to talk to you more from a scientific viewpoint of what we measure. But I think it's important to put it into context why people care. And geomagnetic storms often are caused by things that happen on the sun. We start off often with a coronal mass ejection, something similar, quite large events that then the system elsewhere. And when people talk about space weather, they really talk about how it affects the technology at and around Earth. So there's here. Some of the things that I'm interested in is how things ionosphere changes, and as a result then we get aurora and other atmospheric effects. I like this one because it just says other, but there's loads of things happening in the ionosphere as a result of all this. And we have highlighted down here as well, geomagnetically induced power systems, reception from radio signals, because the ionosphere is changing. And it's really important, I think, that we keep this in mind and study the whole thing as a system, because that's where we find out how it works, really. So this is another why you should care slide, really. And I have the pleasure of talking about this thanks to our colleagues at NASA who have given me this slide. And this is really putting it into context of big spacecraft launches. So if you're launching a rocket or a spacecraft, you don't want to be launching it into high geomagnetic activity, because you can get spacecraft charging and radiation effects as well. But this is primarily because of spacecraft charging, this slide. And this K=4 threshold is often used as a measure for geomagnetic activity. And it's often said that when K is above 4, you have a geomagnetic storm happening. And K=4 in particular was used for the James Webb Space Telescope launch. So this is quite a recent one. And this is for a time interval in 2006 when there was minor geomagnetic storm happening. And you can see there's loads of different lines on here. One of the red ones, which I appreciate, is hard to see, but it's this one here, peaks here in the middle. That's the observed value of K=4. So we know this obviously in hindsight. K=4 in black here, this line is the launch threshold. Another red line, which is the open GGCM model. So that's a global circulation model that has been developed and is run at NASA. Then the lion feather model is also a global circulation plasma model, and then after modeling framework, which tries to model everything from the sun and how the Earth system is affected. And what you'll note here, most crucially, they are all very, very different. So we are missing something here, because we're not able to predict what the observed values are. And you will see in the middle here is a big white box, and this is essentially when it's deemed to be a no-go time, whereas the purple ones are good launch windows in hindsight. So if you were to believe, for example, the blue line, you would have said, oh, here we have a go window, when actually in reality it's no go, because K is at 6 here. So this is quite important to get this right, and this is one of the reasons why I think geomagnetic storms are really interesting, because we know a lot about them, and yet we are struggling to predict when they will happen, and this timing of when things are happening is quite important in the larger scheme of things, because if you can't launch your spacecraft, it's going to be very expensive potentially. So what is a geomagnetic storm? Well, a geomagnetic storm, I already talked about K, but a geomagnetic storm is essentially an enhancement of the ring current. This has been described in those words by Gonzalez et al. In 1994. That was a review paper. The knowledge of geomagnetic storms goes back further, but if you're interested in this, I encourage you to go and read the relevant literature. I'm not going to be doing an all-encompassing review of this today, because it's just not possible. But essentially, these are global events, and they are driven by extremes in the solar wind. If you're interested in what drives them specifically, other than extremes, I would encourage you to look at this other review paper by Kilpua et al. They looked into this, and there are different scenarios on this schematic, looking at the sun in the middle. And if you were traveling, if the solar wind is traveling towards you and you are observing something like S1 to S2, S3 or S4, you are likely to be getting a geomagnetic storm. And so it's often a time when the solar wind is shocked, and then you have a sheaf, or the ejector can be enough, because that's often when you have very, very large IMF values, Southward IMF. As I already said very early on, this drives extremes in the Dungey cycle. So if we have a lot of Southward IMF, our whole system is being perturbed. There's also, you can also get slow stream followed by fast stream. And if you have really fast values of solar wind, you get large values in the solar wind electric field in comparison to the Earth. And so that can also drive a lot of dynamics within the system. In the middle, a schematic from Milan et al. And this is really just to highlight that we do have a global system. And what's colored here in pink is the ring current, which connects to the partial ring current on the night side. And this then feeds into region 2 currents. Region 2 currents are connected to region 1 currents. So the whole current system is connected, it's all working together. And we know that when we have times of high day-side driving or reconnection activity, region 1 and region 2 currents are enhanced. But we also know that when the ring current is enhanced, we also have region 1 and region 2 currents enhanced. So the whole system kind of works together. And that's, yeah, we just need to keep that in mind. So we can measure this enhancement of the ring current by using magnetometers and magnetic indices at mid-latitudes. And this is how it's been done for many years. This is how some of the first geomagnetic storms were identified, and that's what we still do today. And you can convince yourself of this. This bottom here, you can use your right-hand rule to figure out that if you have a ring current going around the Earth, you will see southward deviations in your magnetic field perturbations, especially at the mid-latitude. And that's what we measure essentially, or that's what we look for in the measurements. So how can we measure a geomagnetic storm? Well, we can measure the ring current and the enhancements related to it using space-based observations. This is very, very expensive and difficult to do. There are some instruments that can do this. So for example, the Van Allen probes most recently, they've been working towards building a better understanding of this. But one of the cheapest and easiest ways to do this is to use ground-based magnetometers. And so this is what I alluded to in the last slide. There are a number of geomagnetic indices that have been built to do this, and what they are essentially, there are a number of magnetometers that you put at mid-latitudes, and you can combine the measurements from them to figure out, is this a global deviation in the magnetic field that we're seeing or not? And that then tells you if there's a geomagnetic storm happening. So some of the most oldest geomagnetic indices, one of the most oldest is KP. It's been around for a long time, and it uses a 3-hour cadence. It is on a logarithmic scale. So this is similar to what I showed earlier with the K-index. The K-index is more on a smaller time scale, so a smaller cadence. But KP is really popular with forecasting, and it's very popular in space weather community, mainly because you can get it in pretty much real time. But it's not always so useful for scientific study because we can see deviations in our magnetometer measurements that are very, very quick. And if you 3 hours, that might not be captured very well. We then have the AP index, which is similar, but it's on a linear scale. It also goes back a very long time. And the really good thing with these indices is that they have been continuously measured for a really long time. So if you're doing large analysis, that's really, really good, really useful to have all that data. Then we have the DST index, which is on a 1-hour cadence and on a linear scale. So this is baselined differently, and it's said to measure the ring current more accurately, or the ring current energy rather. And then we have H index, which is similar to DST, but it's on a 1-minute cadence, and this is also on a linear scale. So that's what I'm using today. I'm showing a geomagnetic storm here with SimH, where we've identified an initial phase, a main phase, and a recovery phase. And you can see during the main phase, we see this southward deviation in the magnetic field, then have a recovery phase where it recovers afterwards. And beforehand, we often see this positive increase in the geomagnetic index. And this is telling us that the Chapman-Ferraro currents are likely to be enhanced on the day side of the magnetosphere. We also have SMR index. This is much more, this is a much younger index. And this one is on a 1 minute cadence scale. So that's also linear. It's similar to SimH and DSD, but it's baselined slightly differently, and it uses many more magnetometers. So if you're interested in having lots of measurements, that's a good one to go for. So how do we define a storm? I already mentioned that we're looking for this southwards deviation, and I made my life fairly simple here by using somebody else's criteria. I use H, and I use the same criteria that were used by Hutchinson et al. We're using SimH. The reason why I used the Hutchinson et al. Study for my criteria is because I wanted to look at geomagnetic storms using SuperDARN, and that Hutchinson did. So at the start of all this, I wanted to have a point of comparison, so I thought it would be useful to use that. It turns out it's quite a robust algorithm and very easy to run. So I'm going to be showing data for the most recent cycle, but we have geomagnetic storms lists for going back as far as DST goes back, and it essentially automatically identifies these 3 phases for each geomagnetic storm. The reason why I'm using the most recent solar cycle, so this gray period here, you can see this is the sunspot number of solar cycle, is because the Hutchinson et al. Study, for a start, dates 2008, but also we have some of the most equatorward SuperDARN radars being built in 2006, which means we can measure to lower and, well, to mid-latitudes really. And this becomes important when we look at geomagnetic storms. I will explain what SuperDARN is a little bit later. So we have picked a time period where we have good measurements. We don't have very strong geomagnetic storms during this time period. So you can have no intense storms for my study. We have some moderate storms, a few weak storms. We have less than what Hutchinson had in their studies. But you will see that it's still quite significant and important that we look at these, even though there might be weak storms. So how can we measure the ionospheric response to geomagnetic storms? Well, there are numerous ways of doing this. I won't go into all of them today because that's just not feasible. For a start, you can use space-based or ground-based instruments. You can measure plasma flows, electric fields, electron content, density enhancement, all sorts, all around the system at different, and you can measure different plasma energies, which are all interesting in their own way. One thing, if we want to look at the ionosphere in particular, to keep in mind is that satellite measurements are constrained by their orbits. So if you're interested in the lower ionosphere thermosphere, they have to go really fast not to fall. So especially around the poles, you might also have the problem that your orbit then takes quite a long time. So it's not always ideal for measuring time varying events. Ground-based instrumentation is popular because it can be operated over a long time period and it can provide continuous measurements. And in comparison to spacecraft as well, it is fairly cheap to operate. So that's what I will talk about today. So SuperDARN, what is SuperDARN? You might have heard talk about this before. SuperDARN is a network of radars. It stands for Super Dual Auroral Radar Network. It's a ground-based network of HF radars that were designed to study ionospheric convection. And they've been around for a long time. So the network really started to expand in the 1990s. So we have continuous measurements from then until now. And it's still ongoing. The network is still being expanded today. And the way they work is they send radio signals into the ionosphere. These signals are then backscattered from magnetic field-aligned ionospheric irregularities, and the backscattered Doppler-shifted pulse sequences then allow us to measure the line-of-sight plasma velocity. So in my list here, which I will try and play again. Sorry, I have two screens. So, you will see these fans of each radar. You can see the network is expanding with time. The left is the northern hemisphere and the right is the southern hemisphere. You can largely high latitude built first, followed by the polar cap radars, and then most recently, some of the mid-latitude radars have been added. There's a big project going on in China known as the Meridian Project. They are building more radars there. There's also, what's not shown on here is the Longyearbyen, the Svalbard radar, which has been built since I made this animation. So I think that became operational in 2017. Then it had to be decommissioned for a short while, but is now being built back up. We're also building a radar in the southern Europe, so there'll be another mid-latitude radar as well covering this area here. So we're filling in those gaps slowly. And what we can do with the radars, so we get these line of sight velocity measurements, we can combine those to build up a picture of how the convection in the ionosphere is moving. And so we do some processing of the data there, and our knowledge of vector calculus. We can use this to our advantage to figure out which way the ionosphere is moving. So with this, I just want to say that SuperDARN radar data can be combined to make maps, and the ionospheric variation during geomagnetic storms can be measured with that in space and time. And that's what we're going to do for geomagnetic storms. I have this schematic here again, which is again, to keep in mind that the whole system is connected, and we're looking at a large scale sort of system. The ionosphere that we're measuring with SuperDARN radars really is at the high latitudes here, and it looks like a very small part. But this is why I had in my title the eye of the geomagnetic storm, because the SuperDARN convection patterns that we see, or the measurements that we take from the ionosphere, they are here and they are right in the middle of all this. So understanding how those dynamics work is really crucial to understanding the entire system. And how does this feed into the ionosphere? Well, we have the region 1 and region 2 currents to come in circles. So we have region 1 in blue here, and then region 2 in red on the outside. And this is important to keep in mind because our flows in the ionosphere are shown in black here by these lines. And these two region 1 and region 2 currents, they are essentially boundaries to where we see those flows. So they should line up with our SuperDARN convection. And what, as a result of these field-aligned currents, we have electric fields and we have currents going across they have to close somewhere, so they close in the ionosphere where we have plasma carrying the current. And so as a result of all this, we have this convection, and that can change over time. As I alluded to earlier, the day and night side reconnection rates aren't always balanced, and so our whole convection pattern can expand and contract accordingly. And there's also other asymmetries that can be introduced. And here on the right, I'm showing an instantaneous example, too far, sorry, of the SuperDARN convection maps. And you will see that it's skewed from this ideal schematic in the middle here, and that's often what we see. This is during times when the IMF-BY component was very, very highly positive, and as a result, our convection pattern has shifted here. You will see these black lines here. They are lines of electropotential, but they are also equivalent to the ionospheric flow direction. The little dots show the measurements that we have from the radars at this point in time, and the little colored lines show you which direction the flows are coming from. So these are the line of sight measurements. So these are the measurements made by the radar. And we then do some fitting to figure out this convection pattern. And this takes into account statistical averages as well as instantaneous measurements. So it's kind of an amalgamation of knowledge. So even in places where we don't have measurements, it is still better than taking a statistical average because it's constrained elsewhere by measurements. And so we can look at how this changes during a geomagnetic storm. We can do various things with this, and that's what I will talk about now. So one of the things that I was looking at is where do the fastest flows occur during a geomagnetic storm? We have I took all the geomagnetic storm times and I looked at each individual SuperDARN map, and I took from each map the place where the fastest flows occur. These tend to vary between 200 to 800 meters per second, sometimes even higher. But what you see here is this is just for the initial phase. In each case, we're looking down at the magnetic pole, noon towards the top, dusk is towards the left, midnight towards the bottom, and dawn towards the right. And you can see that during the initial phase, the main phase, and the recovery phase of a storm, this where we see the fastest flows changes. So during the initial phase, we see them quite high latitudes. Expect the throat of the convection pattern to be, so where the flows come in from the day side and start to flow towards the night side. During the main phase, this moves to lower latitudes, and most notably, we see most of these occurrences on the day side now, rather than here we had some on the night side. And then during the recovery phase, it becomes similar again to the initial phase. What I have at the bottom here are two other plots where I've grouped the data by driven times. So this is when the solar wind was pointing southward and going fairly fast, so above 400 meters per second. Kilometers per second, and you can see that it's very similar to periods of the initial phase. It's not like the phase, but there are some similarities in terms of seeing these this activity on the day side. And then we have these enhanced times. So this is just times when the SIMH index was enhanced below a quiet index. And these largely correspond to this pattern largely corresponds to the main phase. So this is interesting. I looked at this in particular because I was interested in seeing how different geomagnetic storms were to generally driven times. And what it's telling us is that there are some similarities, but when you group by initial, main, and recovery phase, you do get some differences still. When you look at the literature, you'll note that these regions where we see the fastest flows are also largely corresponding to where we see enhanced Joule heating. And this makes sense because if you have a fast flow, the Joule heating with the thermosphere and atmosphere lower down is created by a differential flow. We can then look at boundaries. We can measure boundaries with the SuperDARN radar. So when we look at our convection pattern, we can measure this Heppner-Maynard boundary, which is the lower latitude boundary of the flows. And if you remember earlier, this should be where our region 2 currents should be coming in. And then we have the flow reversal boundary, which should match up with our open closed field line boundary. And this should be where the region 1 flows come in. And so what I have on the right here, I've plotted these out for the geomagnetic storms over time. So flow reversal boundary here is in light blue, and the median is shown by a black line. Then we have a lower and upper quartile boundary, also in black. So you can see how trends are changing. And in red, I have the length for the Heppner-Maynard boundary. And so these are the co-latitudes. So if this moves up, it means that this is moving to lower latitudes and our pattern is expanding. Equally with the flow reversal boundary. You can see that the two largely do similar stuff. So during the main phase of the storm, they both expand to lower latitudes. When we look between the two, which see that during the main phase, this offset becomes really, really large. And what that's telling you is that this this return flow region becomes really wide. So you've got return flows happening over a much wider area than you have during the initial and the recovery phase. And we can look at this statistically in a different way. So here I have plotted again the flow reversal boundary on the y-axis against the Heppner-Maynard bound on the y-axis. I'm showing here initial, main and recovery phase separately again. And the pink peaks really show you where most of these points occur. And this line going through it is a simple line of best fit. So this is a linear regression. And if you look at the linear regression, you'll see that these gradients between the three different phases change. So the gradients, this gradient is at a steeper angle than this recovery phase gradient. And what that's telling you is that the recovery, the flow reversal boundary and the Heppner-Maynard boundary are not changing at the same rate. So they're moving together, but one might be expanding and the other one might not be expanding as much. And I thought it'd be interesting to put this all into context with what else is happening in the magnetospheres. So what I have up here, which you'll see when this bar goes away, is my only equation in this talk, which is from Shepard in 2014. And it's a very simple conversion between latitude and L shells. And I know this isn't the best way to calculate it because the whole magnetosphere isn't symmetric. So this is obviously a simplified calculation, back of the envelope type thing. But with this, we can figure out that our flow boundaries, our Heppner-Maynard bound, sits between L shells of 6 and 2.5. Especially during the main phase, it goes to lower L shells, which means essentially that your Heppner-Maynard boundary is going to lower latitudes, so it's mapping closer in. The reason why L shells are interesting is because that's what's used by the part of the community that looks at the closed magnetosphere, so the inner magnetosphere. And one L shell tells you that at the equator, you're 1 Earth radii away from the Earth. So this really comes in quite close during the main phase. And this is interesting because we can compare it to plasma pores and magnetopores motions. This is from a study, Sandu et al. And you can see in this study, the initial, main and recovery phase were grouped in exactly the same way as we grouped them in our study. So the same algorithm was used to figure out where the initial, main and recovery phase were starting. So we're looking at the same thing, and the plasma pores was, plasma pores location was measured using the Van Allen probes here, and the magnetopores location was taken from the Shu model, I believe. And you can see this blue histogram shows you the plasma pores location in terms of L shell for the initial, main and recovery phase. And so what we're seeing here for the initial phase, we are at L shell of just under 6. So that's similar to what we see with our Heppner-Maynard boundary. We then see during the main phase, this moves to lower L shells, so it comes in much closer, and this matches what we see with SuperDARN. And then during the recovery phase, interestingly, it doesn't move as far out as during the initial phase, but this also sort of matches what we see during our recovery phase. The Heppner-Maynard boundary isn't quite at the same latitude as it was during the initial phase. What's interesting is that the magnetopores motion is slightly different. Now the magnetopores motion is further out to the plasma pores. And if you think about where things map to, the region between the magnetopores and the plasma pores really should be where our return flow region is. And so the cavity size variation overall disagrees slightly with the SuperDARN measurements. You can see this here. The change from the initial to the phase is slightly different. And this is the difference between the two. So we would expect to see maybe some changes as we see in this plot here, mirrored here, which we do not. So this is interesting, and we think that this might be something to do with the plasmaspheric plume, but there is more work to be done here to figure out what's going on and how things map as well. Why is this interesting, or why should you care? Well, it either means that the inner magnetosphere inside of the plasmasphere is very compressed during the main phase, or this region is simply smaller in magnetic terms than we think it should be. But based on the boundary measurements that we saw on the last slide, we know the opposite of this to be true. So it really does an open question of how these dynamics fit together. And people often talk about this as a sort of closed system, but I think it's important to keep in mind that what happens at higher latitudes will also affect the mid and lower latitudes, perhaps not necessarily in terms of plasma convecting, because it's at these latitudes it will be trapped on the magnetic field lines, but in terms of the whole magnetospheric morphology, it becomes important. And here I have some diagrams as well from an older study to show you what happens before and after a storm. You can see this is the cold plasma in the plasmasphere. Before a storm, after a storm, it's much eroded and closer in, and really this matches sort of what we see with SuperDARN, which is good. And this is to sort of put it into context with the radiation belt, which will also be affected by all this. So hopefully, if you are studying this, perhaps this might make you more interested in the future in what happens at the higher latitudes as well. So we can do other things with this data set. We can look at morphological changes, and what do we observe? Well, we know that at the very high latitude, ionospheric flows are primarily governed by solar wind driving and magnetospheric processes. That is to say, a lot of it is to do with the what we had earlier on. These electrodynamics are driven by the field aligned currents and the reconnection rates. So the electric fields map from the ionosphere out and vice versa. And so that's what's driving all this. But what do we see? Well, we can take all the SuperDARN measurements, we can put them together, and we can look at what a geomagnetic storm looks like on average. And this is what I'm showing here. I'm showing the first map that I've made for the initial phase of a geomagnetic storm, the start of the phase and the recovery, the start of the recovery phase. These results are all published, and I have animations for this. We've looked at how the morphologies change throughout the storm, so you can go and read up about this if you're really interested. But I've just picked 3 stills here because I think this shows you some of the more interesting features, more crucially, how they change. And the initial phase, you can see our pattern is very small. We have a lot of observations because we've taken all the storms and put them together, but most importantly, we don't have a lot going on here. This is very similar to what we would expect during normal times. Then we move to the main phase, and suddenly things have kicked off. So this is when the geomagnetic index starts to go negative. So this is not when it's reached peak yet. And you can see our convection pattern has already expanded. You can see with really fast flows going on, especially on the side here, which matches what we saw earlier in terms of the statistical location of fast flows. Our convection pattern, just generally speaking, has got stronger. So we have stronger electric fields in our ionosphere as a result. And then during the recovery phase, this becomes even stronger. So now we have an even bigger pattern, and you can see the flows have got a lot faster. And this whole thing really made me think about ionospheric electric fields and how they are captured in models. And it turns out geomagnetic storms are not captured very well. So we've set out to write our own model for this, and we have parameterized geomagnetic storms, and I've written an electric field model for the high latitudes for this, which is just parameterized by SIMH. And we're now in the process of testing this in context, which I will talk about now. So I've picked one example storm to show you all today. It's this one from 2015. You can see SimH goes negative here. It's quite a small storm. It's not, you might not pick it out as a very interesting event, but it is a storm. And here I have the IMF BZ going southward here at around the same time when this goes southward as well. And we have the solar wind conditions, the solar wind speed at the bottom. So you can see it ramps up as we go. Yeah. And I'll not talk about these so much because we're running a bit low on time, I think. So you can ask me about this afterwards if you like. But this is just showing some parameters. This is the Maynard boundary here. You can see it becomes, it moves more equatorward as we go through this storm. And what I want to show you are how these are parameterized or captured in whole atmosphere models. You can see this is should be an animation. I might have to click 1 second. Yeah. Okay. Here we have the time variable ionospheric electric field model, the model that I wrote using SuperDARN data. So this only capturing the dynamics using SimH index. So this is parameterizing essentially the ionospheric electric field using SimH. And it's taking into account the initial main and recovery phase of the storm. And then in the middle, we have SuperDARN data. So this comes directly from the SuperDARN radars. And you can see this moves around a lot. It's not as stable as the solution on the left. And then on the right, I have WAC-MX, which is the whole atmosphere community climate model with ionosphere and thermosphere extension. WAC-MX is a model, is been built to model the entire atmosphere from the ground up. So it starts with very simple things like ocean currents and air movements. And I say simple, but it's obviously far beyond what I know. But it also captures the entirety of the chemistry of the atmosphere and the physics within that. And then to top it all off, on top we have the ionosphere. And obviously at mid-latitudes, the ionosphere is primarily captured, is captured quite well using electrodynamics and our knowledge of how that's changing throughout the day. But at high latitudes, things get more complicated because we have this two-cell convection pattern, or largely two-cell convection pattern, which is more dynamic and changing with different conditions. And that's what you see here, because this is this storm time interval that I've picked. You can see it expands and stronger, but it does so during the recovery phase of the storm, not during the main phase of the storm. So during both the main phase and the recovery phase of the storm. And what notice that this our potential becomes strong. And it turns out that old and based on solar wind conditions, in the sense that they capture the solar wind conditions, but not necessarily bonds. And that's something that we're trying to. So the bottom line here is that main phase of geomagnetic storms are captured poorly, showing you a snapshot. And this is just for a small geomagnetic storm. KP here was only at 3.5, so this is only just about, you know, what most people would consider a storm threshold. It does translate to fast ionospheric flow, so 800 liters per second, and electric fields of around 25 millivolts per meter in some places. The differences are larger as well. And we have a difference in the electrostatic potential of around 20 kilovolts, which you might not think is large, but if you're then looking at plasma flows and how this translates into Joule heating, you have a runaway effect happening. So this is why we have to try and put this into a whole atmosphere model and try and see if it improves our how we capture geomagnetic storms. We also see this difference in the misplacement of the latitudinal boundaries. And this was, I showed you one geomagnetic storm, but this is not an outlier. I've looked at other geomagnetic storms and this is generally the case. So as I said, we are currently in the process of putting these different electric field models into WAC-MX to see what happens. I don't want to jinx it and say it will be better, but hopefully we can capture the physics more accurately, and especially during times of rapid and extreme changes in the ionosphere, and see how that affects the atmosphere elsewhere. So this is my summary. We're looking at geomagnetic storms, and they are really at the extreme end of geomagnetic activity. They create time-varying changes in the magnetosphere, ionosphere, thermosphere system. And really the most important thing here is that the convection pattern in the high-latitude ionospheres moves to lower latitudes. It can move down to latitudes of 40 degrees, and the electrostatic potential becomes really strong. These are not captured appropriately in the models, mainly because a lot of the models are quite old and are not parameterized by geomagnetic activity. So linear interpolation might not always be appropriate as well for the extremes, which is something we have to keep in mind. So we are trying to see what happens when we put different ionospheric electric field models into WAC-MX. That's it for me. If you have any questions, comments, or ideas, please ask away, or if you don't have time today, also get in touch.
Good, thank you so much, Maria, for the very great seminar. And is there any question for her? So you can just unmute yourself or write your question on the chat as you prefer. Okay, see, someone said, great talk, Maria. Oh, it was Alessandra.
Thank you.
Good, so yeah, no questions?
Maybe people are typing.
Yeah, maybe. You can just unmute yourself if you prefer.
Yeah, I mean, we still have 10 minutes, so we can have a little chat. Would you like me to stop the recording, or shall I carry it on?
Oh, just wait a second, just in case there are questions. Okay, I don't see any raised hand or any. Okay, so maybe was that super clear?
Maybe it was really clear, yeah.
Well, actually, I liked so much your summary at the beginning of the introduction. I think that was very great and really helped me to follow everything. So that's, yeah, that was pretty nice. Okay, I see Steve Milan. So how are your statistics affected by absorption of the SD backscatter?
Okay, so yeah, that I think by SD, obviously, Steve, you mean SuperDARN. Yeah, so with the SuperDARN radars, they are, just for the benefit of everyone, they are transmitting almost all the time, but we don't always get backscatter. So in order to get backscatter, you need irregularities in the ionosphere, and that's obviously not always happening. This is a good question because there's been some studies in the past that have shown, and obviously I think Steve, you were involved in those, that have shown that during auroral substorms, because the aurora changes the ionosphere, you get absorption in the ionosphere, and so you don't get backscatter. But actually what I found is that during the main phase of the geomagnetic storm, we tend to get more backscatter. It's only in the recovery phase when this starts to happen that we get more absorption and less backscatter. It might be to do with the fact that we are measuring a larger range of latitudes than we used to, but I've certainly not found that the backscatter decreases during the geomagnetic storms. Yeah, so that's a good question.
Good, so I think Steve also said there were some papers sorry, there were some papers on storm time BS statistics by Megan Gillis on this topic.
Yes, yeah, I am aware of those.
Good. Any other questions for Maria? I don't see. Oh, Steve said, good. I don't see any raised hand or any other comment. So maybe we can stop in here if that's okay for everyone. So thanks again, Maria, for your very nice talk. So it will be, I will upload this most probably tonight because I'm in a conference today. So most probably tonight I will upload this to YouTube for the rest of the people. And also I want to do a general announcement. So next month, so we still don't have anyone to speak for our next mixed seminar. So if you know of someone who would like to give a talk, or you know of any topic that we are not covering, please send me a message or send a message to Maria or anyone in the Mist Council so we can arrange to have a seminar. Otherwise, we will have just a month of holidays for the seminars. So yeah, thank you very much. Sorry, thank you so much again, Maria, and see you all soon.
Thank you.
Yes, you can stop now.